This is the ultrasonic sensor principle simplified by Dave Corpy. Here is a classical specification for an ultrasonic transducer for the purpose of measuring flow within any acoustically conductive fluid. Almost everything is acoustically conductive. This is what an ultrasonic clamp-on looks like. It consists of some electronics, cables that connect the electronics to the sensors, and the clamps that hold the sensors to the pipe on the outside of the pipe. Also, so you can have an understanding of the difference in sound speed. The sound speed in water is 1,400 meters per second. The sound speed in air is 340 meters per second. Sorry, 1,480 meters per second versus 340. That's why when we're underwater and somebody taps their scuba tank, we can't tell which direction they are. Our ears are not far enough apart, and our brains are too slow to determine where they are. An acoustic sonar, that's what these things are. An acoustic sonar transducer, which is an ultrasonic beam that passes through a pipe at a particular angle. And here's a configuration. Here's the typical equation. I'm going to give you the big fat overview first. There's two different ways used in acoustic, the ultrasonics. One is directly from one sensor to the other, and another one is from one sensor bouncing off the wall, just like a billiard ball, equal angle, will bounce off to the downstream sensor. This is the 50,000-foot view how these things work. Imagine swimming. I'm gonna let you look at this picture. Swimming down a pipe. If you're swimming and the water is still, the velocity you can swim, if you're a perfect swimmer, is this when you're going down. And when you're going up, it's the exact same. Now what happens when the flow goes, we send an acoustic pulse down. This is 1 megahertz pulse. It's got a little 45 degree. Snell's law takes the shortest route in the steel or whatever it is. And then within the pipe, let's say it's water, the acoustic wave travels down. And this transducer senses how long it took to go from ping, ping, and times the time sense. Then this one goes ping, and this guy goes pong, and he tells what's the distance. So what we're doing is we're measuring the time of flight from this transducer to that transducer through this medium. Could be a pipe, could be cast iron, could be rubber, could be plastic, could have a liner. As the acoustic pulse travels through this metal, it's going to go faster in the metal than it will through air, so it's going to take a shorter path, and it's in this other medium. Say this is air, it's slowing down and takes this angle. So this theta angle, this is where we got the, this is the transit time of the ultrasonic beam. This is the diameter of the pipe, d. This is sine 2 theta. Here's delta t, the distance it takes time to go from here to there. The difference between the upstream and downstream, if it's zero, there's no flow. And the time that is to go down and the time to go up. So what's really important in this is that these transducers be spaced precisely apart from one another. If they're off, and where we can gain our claim of accuracy is based on how accurately we place these transducers. That's the advantage of this particular mounting structures, because a person can take a caliper, and the system will tell you what the distance must be based on this pipe diameter and this pipe thickness, so that the transit beams will go from one to the other. So that's the really important part. And I give this because people get confused about how these things work. They confuse them with mag meters. They're not anything like a mag meter. A mag meter requires electrically conductive material, and this requires acoustically conductive material. It's like the way bats fly. We're measuring the time distance, so we have, you can read this. This is the simple equation. We don't really have to know how it was derived and such, but you can take the math of it, and it's probably easiest from this one. Remember, these are called transducers because one is a transmitter then it's a receiver. So this transmits a pulse, sends it down. This guy says when it got it. This guy says, I'm going to send one now to you. And this guy says when we got it. We're going to compare those two times. We're going to measure the total transit time of the ultrasonic beam in the fluid that we're flowing. It's different in water and air, as we saw here. It's 4 times faster in water than it is in air. We know what that is. And that is determined by the fluid media. Delta T, and these times are easy now for us to measure. We have temperature-controlled crystal oscillators that are given to us from GPS by the government. We can measure to 1/10 of a millionth of a microsecond with extraordinary accuracy with these things. So we have, we want to show the 2 different methods. This is the most common method we will suggest that folks use, from 1/2 inch to 16-inch pipes, most commonly used. And then this explains why you would use this kind of system. If the signal's poor, or you're measuring the flow in greater than 8-inch, or measuring flow in cast iron pipes, you would be using this kind of direct shot, not a ricochet like this, but the direct shot. The beauty of this is the transit times are a little longer, and you get a little more, less uncertainty by your transit time calculation. You wouldn't want to have to determine how long it took sound to travel in a 1/2 inch pipe when these guys are shooting across each other. That's the benefit of this orientation. So also, I just wanted to show you Snell's law tells us how the acoustic wave travels through the material. As you send the acoustic wave, which was angled at 45 degrees from the transducer, it hits the pipe. There's some coupling material that keeps this acoustically connected to whatever it is. And then the sound travels, and you can see that it bends. So this is Snell's law. It tells you what it is. And if we did have a liner in here, we would take that into account too. Normally they're rubber, and they're really slow, so sound travels really slow through rubber. So it'd take this long edge like this, and so here's the equations for Snell's law, and that is it. And I hope that helps you understand why the benefit of these. The downside of these is that if you're not wonderfully careful how you place the transducers, because you're placing these on your pipes, and you don't follow the instructions precisely and use a micrometer to get the distance between these 2 faces, that's what they're referred to, and you don't clean the contact between these sensors, it's not a wonderful thing. The signal is weak, but the distance is critical, because that's how we're determining the D, the transit time within the D. So we're looking at the velocity within the D. And also, these things are nice that they're slightly averaging. They're taking over a path, but they don't like swirl, and they don't like air bubbles. So that's why we say up on the top here, acoustically conductive fluid with less than 5% air bubbles or solids. Those confuse it, and things ricochet off and get things all messed up. So there you go. You can go to the website, Tactical Flow Meter, and look at these ultrasonic clamp-ons, and they are a wonderful choice for lots of applications. Thank you very much.